lecture 9 part 2. So in part 1 we have started discussing signal flow graph, and we have discussed that path and forward path. So today we will see some more terminologies which are used in signal flow graph. So one is that loop. A loop is a path that originates and terminates on the same node, and along which no other node is encountered more than once. So a loop is a path that originates and terminates on the same node, and along which no other node is encountered more than once. So this is that definition of loop. So let us just draw the signal flow graph that we have done in previous part 1. So here we have that node y1, y2, y3, y4 and y5. So here again you can take that this is y5 output node and this is input node. This one is input node, and the signal flow graph that we have considered in part 1, I am drawing it again. So whenever you will be drawing that signal flow graph, should not forget to mention that arrow, because that arrow indicates that the flow of signal. And there is one path here, so that is A25, that branch gain, A34, A24, this is that self loop, and A23, A32 and A12. So this signal flow graph already we have discussed in detail in part 1. So now here let us see how many loops are here. So one loop is, you can see here, that is y1, y2, y3 and y2. So this is one loop, that is y2, y3 and y2. We have another loop, that is y3, y4 and y3. We have another loop here, that is y3, y4, y3. Then here there is another loop, so we can write that y4, y4. Is there any other loop? No. So in this case we have only 3 loops. Yes, we can have another loop that is, say, this y2, y4, y3 and again y2, that is y2, y4, y3 and y2. So this is actually the definition of the loop. The loop is a path that originates and terminates on the same node. Here you can see that it originates from y2 and terminates at y2. The same thing happens for other cases, other loops as well. And no other node is encountered more than once. So that is that important, because if you consider that y2, y3, y4, y3 and y2, so this is not a loop, because you can see here that y3 is encountered more than once. So these are the 4 loops exist in this particular signal flow graph. So let us see the other definitions. What is path gain? We have seen what is path. So now the path gain is the product of the branch gains So here you can see, so these all are the branch gains, A24, A34, A23, these all are the branch gains. So the product of the branch gains encountered in traversing a path is called the path gain. So if we just consider a path in this particular example, suppose we are considering a path, say y1 to y2, then y3, y4, y5. So that is y1. Here you can see that this is y1 to y2, then y3, then y4 and y5. So this is that path. So then how many branch gains are there? So this is one branch gain, this one and that one, and here I think there is one branch gain, y4 to 5, that is a4 to 5, here a4 to 5. So then what would be the branch gain, path gain? So path gain is the product of branch gains. So that is a12 here, and then a23 here, a23, then a34, and a45. So that means the product of the branch gains encountered in traversing a path is called the path gain. So whenever you have a signal flow graph, you just first identify which one is that path and then just take the product of branch gains, so it gives you the path gain. Now what is non-touching loops? Non-touching loops. 2 loops of a signal flow graph are non-touching if they do not share a common node. Of a signal flow graph abbreviated as SFG are non-touching if they do not share a common node. So let us see in this particular example, is there any non-touching loops or not? We can see here that one loop is say this loop. So this is that loop. This is that loop, that is y2, y3 and y2, and here there is a loop. So you can see that this particular loop and this loop, these two loops, they do not have any common node. So then we can see that in this particular example we have a pair of non-touching loops. So that is y2, y3, y2. So this is one loop, and another loop, that is the self loop, y4. So these are the two loops which are actually non-touching loops. So in signal flow graph we will be using these terminologies. So one is that path, then forward path, then that loop, path gain, and non-touching loops. Whenever we solve some problems in signal flow graph, we perform some signal flow graph algebra. So these are very simple. So let us see what is that signal flow graph algebra, that SFG algebra. These all are very simple. Just if you apply your common sense and if you just apply that signal flow graph terminologies and ideas, then you can easily find out what are the relations must hold applying that signal flow graph algebra. So let us see, if you have a node like this, and suppose there are many branches. So there are many branches. So these all are the nodes. There are many branches. So nodes are here. This node is y1, then y2, y3, y4, y5, y6 and y7. So you need to put that arrowhead because that signal is flowing like this, suppose. So here we just put the flow of signal in reverse direction, this one, and we need to mention that branch gain as well, which is also very important. Whenever you will be drawing that signal flow graph, do not forget to write that branch gain, that is A41, A51, A16, say A17, A21 and A31. So here you can see that what is y1, that thing already we have seen at the very beginning, that is y1 equal to A21. So this signal is coming like this, that is A21 into y2, then A31 into y3, then A41 into y4 plus A51 into y5. So as in those two branches signals are going out, so basically we should not consider that one in this particular algebraic equation. Then we have another algebraic equation, that is y6. So y6 equal to A16 y1 and y7 equal to A17 Y1. So you can see here these three algebraic equations represent this signal flow graph, or in other way, from this signal flow graph you can have these three algebraic equations. So now the second one is, if you have a signal flow graph like this, so in between two nodes, if you have multiple branches, suppose you have three branches and A, B and C. So this can be represented as, this is Y1, this is Y2, and here that would be A plus B plus C, which is straightforward. If you just write here that Y2 would be equal to A Y1 plus B Y1 plus C Y1, from there easily you can find what would be that effective branch gain. Similarly, if you have say four nodes like Y1, Y2, Y3 and Y4, and suppose you have A12, A23 and A34, signal is flowing like this. So then in this case you can see here that from Y1 to Y4, Y4, and the effective branch gain, or you can say that from Y1 to Y4 this is a path, so basically the path gain would be A12, A23, A34. So these are actually the signal flow graph algebra. Whenever you will be solving some problem, or if you want to find that transfer function from signal flow graph, we'll be using these algebras to simplify that signal flow graph. So now we'll be discussing an important result of signal flow graph, which is called that Mason-Gain formula. So this Mason-Gain formula is used to find the transfer function from a signal flow graph. So this is a very important result in control systems, linear control systems. So let us start discussing that Mason's gain formula. So Mason's gain formula. So this formula is used to find the transfer function from signal flow graph in between any two nodes. So this Mason-Gain formula states that if you have one output node, that is Y out, and if you have one input node, so the gain between the input node to output node, from input node to output node, is summation of mk delta k by delta, where k equal to 1 to n. So now we will be discussing in detail that what is this m, what is this mk, delta k and delta, and what is n. So n is the total number of forward paths. N is the total number of for, so already we have seen what is forward paths, total number of forward paths between Y in and Y out. So that means in signal flow graph, if we are interested in to find what is the gain from Y in to Y out, so first we need to identify how many forward paths are there in between Y in and Y out. So N is the total number of forward paths between Y in and Y out. So now what is Mk? So Mk is gain of the kth forward path. So we can see it here as k is from 1 to n and n is the number of forward paths. So Mk is the gain of the kth forward path. Now what is delta? This delta. So delta is equal to 1 minus sum of the gains of all individual loops plus again bracket sum of the products of gains of all possible combinations of two non-touching loops already we have seen what is the definition of non-touching loops, then minus, you can see here the sign minus, then plus, then minus, again the same thing, that means the sum of the products of gains of all possible combination of three non-touching loops and so on. So then again sum of the products of gains of all possible combinations of four non-touching loops and so on. So this is actually delta. So here you should note down that the symbol is coming like minus, then plus, then minus, again plus, then minus, like that. And here you can see that sum of the gains of all individual loops, then the next one is two non-touching loops, the third one is three non-touching loops, then four non-touching loops, like that. Then what is delta k? Because here you can see that there is one term which is delta k. So delta k is the delta, that means this delta for that part of the signal flow graph that is non-touching with the kth forward path. I think this particular Masson-Gain formula would be clear whenever we see one example. So let us first see that example, then if you have any doubt, I will be discussing it again. So let us take one example first. So first draw that signal flow graph. So there are 7 nodes, that is y1, y2, y3, y4, y5, y6 and y7. So 7 nodes, and we have the branch from y1 to y2 with gain 1, then another branch here that gain is g1. So here you can see this g1 is actually the transfer function. You have another gain that is minus h1. So now actually I am replacing the gain with the transfer function. That means from node y3 to y4 the transfer function is g2, and as you know, we have already pointed out that those nodes are basically the variables. So now from y4 to y5 the branch gain is g3, and there is one feedback, so this is h2, and here you have another gain that is g4, and here the gain is 1. So in y6 there is one self loop with branch gain minus h4, and from y3 to y6, from y3 to y6 there is a branch with that gain g5, and from y5 to y2, from y5 to y2 we have one feedback path with gain minus h3. So we have taken one example, just arbitrarily we have taken one example, and this is that signal flow graph. Now our objective is to find what is the transfer function using Mason's gain formula. So as we have seen already that in Mason's gain formula, if you just look at that Mason gain formula, so we need to find how many forward paths are there. So that is our first objective. How many forward paths are there? So let us see the forward paths. Forward paths. So one forward path is y1 to y2 to y3 to y4 to y5 to y6 to y7. So this is one forward path, that is y1 to y2 to y3 y4 y5 y6 y7. We have another forward path, that is y1 to y2 to y3. So that is y1 to y2 y3 to y6. You can see here, you can also follow this path, y6 to y7. That means from input to output. So we have another forward path, that is y1 to y2 to y3 to y6 to y7. Do you have any other forward paths? No. So what is the forward path gain? So the gain is forward path gain. So for this first forward path, you can see here 1 into g1 into g2 g3 g4. So that is g1 g2 g3 g4. So if we say that this is first forward path, the gain is this one. And for second forward path, we have that gain 1 into g1 into G5 into 1. So only G1 into G5. So in this case, that gain is G1 into G5. So now, if you look at the Mason-Gaines formula, so the Mason-Gaines formula says that summation of k to n. So here in this particular example, n equal to 2, because you can see here you have only 2 forward paths. So the Mason-Gaines formula says that this n and summation of k1 to 2, because you have 2 forward paths, mk delta k by delta. So if we expand it, it would be m1 delta 1 plus m2 delta 2 divided by delta. So now let us see what is m1. So if you look at the definition here, so mk, that is m1, is the gain of the kth forward path. That means m1 would be the gain of the first forward path. So the first forward path gain is here. So we can write that this is G1, G2, G3, G4 into delta 1. And what is the gain of the second forward path? That is G1, G5 into delta 2 divided by this delta. So now just look at what is delta 1. So delta 1 here, delta 1, the delta for that part of the signal flow graph that is non-touching with the kth forward path, that is non-touching. Or we can, okay, so first we do that delta, then we'll be coming back delta 1 and delta 2. So let us see what is delta. So delta equal to 1 minus, so let us see, first you write that delta equal to 1 minus sum of the gains of all individual loops. So how many loops are here? Here you can see this is one loop. Now this is another loop. Then we have another loop here. Then 3 loops. We have another loop here. So 4 loops. And is there any other loops? So we have 4 loops. So now if we write that sum of the, this is sum of the gains of all individual loops. So if we look at the loop 1, so suppose this loop, particularly this loop, so the gain is minus G1 H1. So here we'll be writing minus G1 H1. So let us see the other loop. So this one, so that is G3 into minus H2. So that means G3 minus H2. So then we have this bigger loop, this bigger one. So that is G1, G2, G3 minus H3. So that is G1, G2, G3, then H3. So minus sign I have taken here. And we have another individual loop, that is this one. So that is minus H4. So then we have done the first part. This part is done. So now let us see this part. Sum of the products of gains of all possible combinations of 2 non-touching loops. So here we have already seen there are 4 loops. So now we can see here that this loop, that loop, and this loop, they are actually non-touching loops. But if you look at the bigger loop, so basically this loop and that loop, they are inside this loop, so they are not non-touching. But if you look at this bigger loop and this small loop, self loop, they are non-touching. So let us see how many combinations we can have. So the first one is, so just take this one and that one. So then what you have, G1 minus H1, then G3 minus H2. So minus minus plus, so that means you can see the formula here, that is plus. So I write this plus, then product of 2 non-touching loops, so that is G1 H1 G3 H2. So then we have another combination, say this loop and that loop, so that means G1 minus H1 minus H4, so that means G1 H1 H4. So we have G1 H1 H4, and then again there is another combination, this loop and that loop, so here G3 minus H2 minus H4, so that means G3 H2 H4, so that is G3 H2 H4. Now there is another combination, that means this bigger loop and this loop. So here you can see that G1 G2 G3 minus H3 minus H4, so that is G1 G2 G3 H3 and H4. So no more combination is available here, so that means this part is done. So now the third one, that means the sign is minus, so the sign is minus here, we can write it here with different colors, a minus. Then it would be the product of sum of the products of 3 non-touching loops. So here I can see that means this is one loop, this is another loop, this is another loop. So 3 loops are actually non-touching. What is the product? Product is G1 minus H1, G3 minus H2 minus H4. So that means only one term is there, which is minus minus plus, then one minus remains. So that means here you can see that minus G1 H1 G3 H2 H4. So as there are only 4 loops and we cannot have 4 non-touching loops, so that means we can stop here, because only you can have 3 non-touching loops in this particular signal flow graph. You do not have 4 non-touching loops, so delta ends here. So this is actually that expression for delta. So now what is delta 1? So delta 1 is, here you can see delta 1, that means is there any loop, you can see it here. So delta 1 corresponding to first forward path. So the delta for that part of the signal flow graph which is non-touching with the first forward path. But as the first forward path is this one, so this one is the first forward path, you can see that this particular loop, this loop and that loop, all 4 loops are touched with this forward path. So that means delta k equal to only one, because the other terms does not exist. So here delta 1 equal to 1. Now let us see what is delta 2. So the second forward path, if you look at here, the second forward path is this one. So the second forward path is this one, that means here only there is one loop which is non-touching with the first forward path transfer function. So that means here the delta would be, that means this is the delta for that part of the signal flow graph. So that means this is that signal flow graph, and you can see here this is the part which is non-touching with the kth forward path. Kth here actually k equal to 2. So that means this is the second forward path, and only this part of the signal flow graph is non-touching with this forward path. So there is only one loop. This is that loop, and its gain is G3 into minus H2. So here you can see the delta 2 would be equal to 1 minus, that is G3 into minus H2. So that is 1 plus G3 H2. So this is delta 2. So now what is the Mason gains from Y in to Y out? So we can write it here, the Mason gains, that M is equal to that this one. So that is G1, G2, G3, G4, the first forward path, delta 1 equal to 1, and then G2, sorry, that is G1, G1, G5 into delta 2. So delta 2 we get, that is 1 plus G3 H2, that is in numerator, and in denominator you have the delta. So what is the delta you get? This one, that is 1 plus G1 H1 plus G3 H2 plus G1 G2 G3 H3 plus H4, and then you have G1 H1 G3 H2 plus G1 H1 H4 G3 H2 H4 plus G1 G2 G3 H3 H4 plus G1 H1 G3 H2 H4. So this is actually the transfer function. This is the transfer function from this particular node to this node, that means from input to output. So whenever a signal flow graph is given to you, applying Mason-Gains formula, you can find the transfer function. And the beauty of this particular formula is you can see without writing any algebraic equation, just by identifying forward path and loops and non-touching loops, we can write directly the transfer function. So now another important thing is, if I ask you what would be the transfer function from y1 to y2. Suppose this is given and you need to find what is the transfer function from y1 to y2. So as we have already discussed, that means you can make any node if it is not an input node. So you can make that node as output node. So I am making this node as output node. So this is that output node. So now our objective is to find what is the transfer function from y1 to y2. So if we apply the Mason-Gains formula, what we need to find? First we need to identify what is the forward path. So here actually only one forward path is there. So this is that forward path, that is y1, y2, y2. And what is that gain, forward path gain? So forward path gain is here 1 because this is also 1. So now you can directly apply the Mason-Gaines formula to find the transfer function. And here another important thing you can see, that if you are asked to find what is the transfer function from y2 to y7, so that means if I choose any node inside that signal flow graph, suppose if I choose this node and if I ask you what is the transfer function from y3 to y7, can you find it using Mason-Gaines formula? So there is a technique of finding transfer function from any node inside that signal flow graph to the output node. So here you can see that this particular transfer function you get, that is y7 by y1. So here you can see this is that signal flow graph, y1 is here and this is that y7. So this thing already you get. So now your objective is find y7 by y2. So you need to find the transfer function from y2 to y7. So here you have that y2 and here you have y7. And you can notice here this y2 is not actually that input node. It is a node inside that signal flow graph. So here easily you can find that y7 to y2 is nothing but, you can write that y7 by y1, then again y2 by y1. So then you can see that this is actually from input node to output node, and here again you can write that this is input to another output node, because you can make this y2 as output node as I have done it. So then let us find what is y1 to y2. So let us first find what is the transfer function from y1 to y2. So now you have seen that this is that forward path. So this one is that forward path. This is that forward path and its gain is 1. So now what would be the delta? So delta remains same. The reason is, here you can see that if you see the Mason-Gaines formula, so this delta remains same for a given signal flow graph. So in this particular case, this signal flow graph remains same, so delta remains same. Only thing is, in the numerator part, as there is only one forward path, but this is the rest of the portion of the signal flow graph, here you can see, which is actually non-touching with this forward path. So in this particular part, you can see that there are two loops. This is one loop and this is another loop. So two loops are there, and again they are non-touching loops. So we can find what is the delta 1 in the numerator. Let us see what is that. So here y2, the forward path gain is 1. So now what is the delta in the numerator? First 1 minus, because we will be again applying this particular formula. So 1 minus sum of all individual loops. So here how many individual loops are there? So two loops are there. This is one loop and this is another loop. So sum of, so here the gain is minus G3H2 and here gain is minus H4. So that means here minus G3H2 and here you have H4, and then if you see the third term, so this one, so that means this is minus and no, sorry, so third terms is this one, so this is plus, and you have two non-touching loops. Here you can see that two non-touching loops. So plus this plus into two non-touching loops here in this particular signal flow graph. You can see this is one loop and this is another loop, which are actually non-touching loop. What is that product? Product is G3 into minus H2 into minus H4. So that is G3 H2 H4. So there is no three non-touching loops, so that means delta ends here, and then you can see the same delta will be here because you have that same signal flow graph. So that means y2 by y1 is equal to 1 plus h4 plus g3h2 plus g3h2 h4 divided by this delta. So now easily we can find what is y7 by y2. So here you can write it here that y7 by y2 equal to y7 by y1 divided by y2 by y1. And what is y7 by y1? So here you can see that this is that numerator, and in the denominator, so this is equal to delta, and here also the same delta is here. So basically your y7 by y2 is this particular term divided by this particular term, because delta will be cancelled out. So that means you have here G1, G2, G3, G4 plus G1, G5, 1 plus G3, H2. So this one is this thing, and you have in the denominator 1 plus H4 plus G3 H2 plus G3 H2 H4. So this is the method you need to follow for finding transfer function using Mason-Gens formula. Whenever you have some other, if you are asked to find transfer function from any node inside the signal flow graph to say output. So today what we have seen, so we have actually discussed some terminologies, that is that loop and then path gain, non-touching loops, and we have seen that signal flow algebra, and then we have discussed in detail that Mason-Gens formula, and we have understood the Mason-Gens formula via one example, and this is that signal flow graph. And here we have again discussed, that means if you are asked to find the transfer function from any node inside that signal flow graph to output node, how to find the transfer function. So this is that method you need to follow. So this is that method you need to follow. Thank you.